So good morning, everyone, and welcome to the session. I see Professor Hong is online, so let me make a start. So, as I say, welcome to the session that we have this morning. We have two excellent papers this morning, and the first of these is from Professor Cheng-Yu Hong, who is from the School of Civil and Transportation Engineering at Shenzhen University in China. Just to say a little bit about Professor Hong's background, he received his doctorate from Hong Kong Polytechnic University. He's director of the Geotechnical and Underground Engineering Laboratory and Deputy Director of the Intelligent Infrastructure Research Centre and Deputy Director of the Key Laboratory of Green, Efficient and Intelligent Construction of the underground metro stations. So again, I think an excellent application of some of the areas of environmental monitoring. He's been widely involved in industrial projects, some 20 industrial or commercial projects, and fiber optic sensor related consultancy in this field. So we look forward very much to what Professor Hong has to say about some of the work on fiber optic sensors in this exciting and challenging area. So Professor Hong, over to you.
Okay. Thank you very much, Mr. Chairman, for the kind invitation. Well, first of all, I want to thank the organizing committee of the conference for the kind invitation. And since my major is in civil engineering, so my topic is the performance monitoring of underground structures using fiber optic sensors. And okay, first of all, I want to introduce the research background. We all know that in mainland China, especially in some major cities, we have found many different types of geotechnical failures. So these photos are typical foundation failures. As you can see that each engineering failure accidents led to significant economic loss, sometimes maybe led to significant casualties. And also another major area that fiber optic sensors may be used is for the landslide monitoring. So here I listed some typical landslide occurred all over the world. And in Shenzhen in 2015, there was one serious accident occurred in Guangming district. More than 33 buildings were destroyed in this accident, and finally around 80 people, 80 casualties were found in this serious accident. We have also found some other accidents, that is engineering failures in tunneling projects, like the typical tunnel collapse in Japan, Germany, Brazil, and in Hong Kong and Macau in China. So normally these kind of failures are serious and led to significant economic loss. And where for piles, as we all know, that is a kind of typical structure which is used for supporting upper structures. So that normally the pile failure may lead to significant failure of the upper structures, like the pile foundation failure in China, Shanghai in 2009. So the pile failure led to the total collapse of upper structures. So also in terms of the recent articles in some famous journals and also some famous books, we found that the sensors, especially the fiber optic sensors, will be a very promising technology for monitoring underground structures. So here I will simply introduce the typical fiber optic I used in geotechnical monitoring. First of all, the FBG sensor is fiber Bragg grating-based fiber optic sensors. So it's typical point sensors which can be used to measure the strain, force, temperature, pressure, or shape of structures. So the typical advantages of these sensors for geotechnical monitoring is very small size and lightweight, so that it can be easily embedded for typical underground structures, like it can be easily embedded inside concrete or just simply mounted on the steel bars. And the measurement principle is quite simple, just to measure the strain or temperature in terms of the central Bragg wavelength change, and the external variation of strain or temperature led to a linear change of the central Bragg wavelength. And another typical technology I used for field monitoring study is the optical frequency domain reflectometry. It's a typical technology which is normally used for the analysis of optical light pathways and the reflection characteristics in the fiber optic sensors. While the main advantage of this kind of sensor is it can measure the strain or temperature change of the underground structures at very high spatial resolution. The minimum spatial resolution can approach sub-millimeter resolution, so it's quite it has a very a high spatial resolution, and the maximum measurement range can approach up to 200 meters. So it can be used for monitoring most large scale structures underground. But the last technology I used is the Brilliant optical time or frequency domain analysis technique. The measurement principle is quite similar to the previous OFDR technique. Well, the main difference is that the spatial resolution is relatively lower. That is normally is between 20 centimeters and 50 centimeters, while the maximum measurement range can approach 50 kilometers. So it can be used for measuring very large scale infrastructures. And next, I will introduce some typical monitoring studies using fiber optic sensors for typical geotechnical structures. First, I will introduce the PAL monitoring using fiber optic sensors. So the main technology I used in this case is the BOTDA in the BOTDA technology. So the as we all know that BOTDA technique is a fully distributed measurement method, and in here we measured the movement of a typical pile wall here. So we can see this typical concrete pile wall, and one side of the concrete pile wall was under construction, so in this area, so we wanted the movement of the whole wall. So in this study, we used fiber optic sensors to monitor three typical piles here is including the number BP5, BP19, and BP28, and the length of these piles were 33 meters, 42 meters, and 48 meters. It's quite long, and while the diameter is was 2.5 meters in this study. And this photo shows typical fiber optic sensors installed in field here. So we have some protection box, and we place fiber optic sensors inside these boxes for pile monitoring. And in this study, we have measured the distributed strain from the pile height to the pile tip. And in this curves, we found that in this the obtained strain distribution of the three piles were symmetric. That is, here is pile tip, and the other two ends were the pale top position. So it's symmetric. That is, we placed the fiber optic sensor from the pale top to the tip and back to the top, so that the data curves were symmetric, is reasonable. And also we can calculate the pale deflection in terms of the distributed stream from the pale tip to the pale top. And we can make comparison between the measured deflection using the fiber optic sensor stream with the and the obtained movement data of inclinometers. And another monitoring study is used fiber optic sensors to monitor the a total of 4 pale behaviors during construction process. In here, we have selected 4 different pales, and we used also the FDA technology for monitoring the pale stream distribution. And the fiber optic sensor was also mounted from the pale top to the pale tip and back to the top. So the whole process is quite similar to the previous case. And we measured the strain distribution and also calculate the axial force distribution, also the bending moment and the frictional resistance of these piles during the construction process. So this kind of study is very limited, because we had to monitor the pile behavior in a relatively long term, at least 4 years in this study. So these photos show the installation process of the sensors and how to the process of the installation of the steel cage underground, and also the protection box after the pile were constructed in field. And we have collected the pile string data for more than 2 years, and we have obtained the we have also taken a number of photos of the field, indicating that how the change of structures above these piles. And we found that the piles were under continuous but limited vertical compression. That is, we found that the strain rate against time in this study is quite limited, is around 0.6 microstrain each day, and is under compression, while the maximum measured strain of the pile were less than 210 microstrains. So that's what fiber optic sensors can indicate in this study. And also another 2 piles, another piles number A43, that is, we have also observed similar phenomenon, that is the strain change of the pile, and also the maximum deformation of the pile can also be obtained using fiber optic sensors. And also the conclusion can also be drawn here, that the pile deformation is still limited. That is, the pile is relatively safe in this during this construction period. And also we have carried out another pile monitoring work in another project in Shenzhen Luohu. So normally for piles, sometimes we have to examine their pull-out resistance or the loading behavior in compression tests. So conventional sensors just the point sensors cannot obtain the distributed strain. So in here we also used fiber optic sensors to monitor the strain distribution of 2 pull-out piles and 2 piles in compression tests. And also the pile dimension were 26 meters in length and 1 meter in diameter. And these are the photos showing the installation work of the fiber optic sensors, and also this is typical the compression test and the pull-out test of piles. And we already installed fiber optic sensors inside these piles. And we have obtained the loading behavior of the pulse. And the typical curve of a pulse obtained in this test is the relationship between displacement and vertical load. And also we have obtained the distributed strain from the pulse head to the pulse tip and back to the pulse head. And in terms of the measured strain distribution, we can obtain the axial force change of the pulse and vertical compression of the pulse, and also the contribution of different substrate layers underground. And this is very difficult for conventional sensors to obtain for engineering, and also the we can further calculate the mechanical parameters like the axial force bending moment in terms of the distributed strain, so that the mechanical behavior of the pulse can be well understood using fiber optic sensors. And we also make a comparison between the measure from conventional displacement transducers and the displacement calculated from the distributed strain of fiber optic sensors for the 3 pulse. And most of these figures show that the two displacement agree fairly well between the 2 types of sensors. So this also indicates that the fiber optic sensor is quite effective for the deformation monitoring of large-scale gel structures here. And the next is I will choose some typical applications of fiber optic sensors for slope monitoring, also some reinforcements for slopes monitoring, like the saw nails, anchors, or gel grades. Well, for slopes, normally we have to monitor the slope movement or the mechanical behavior of the reinforcement embedded inside slopes, like saw nails. So in this study, we have installed a total fiber optic sensors on total more than 70 saw nails and 11 inclinometers within 12 slopes in Panjshir province. So we just simply installed FPG sensors along the 2 sides of inclinometer tube to measure its lateral movement. And also we have embedded FPG sensors at some specific locations along these saw nail bars to measure the elongation change of saw nails. Well, we have obtained the movement of the slopes in terms of the distributed strain obtained from the inclinometers, and also we can obtain the strain change of all these saw nails. And in terms of the strain variation or the movement variations, we can use this data to understand the slope condition. And also we have monitored some new types of saw nails in slopes. That is, a new type of saw nail is GFRP bar saw nail. So it's a typical new material used for slope reinforcement. The GFRP refers to the glass fiber reinforcement polymer. And in this study, we measured the distributed strain of 2 types of GFRP bars embedded inside slopes. So diameters were 25 millimeters and 40 millimeters. So these photos show the installation method of fiber optic sensors on these bars. That is, we use clamps to fix 2 ends of the fiber optic sensors on the bar surface. And in calibration, we also obtained the frequency change of fiber optic sensors against fiber optic sensor distance. And we obtained the frequency change of the fiber sensor position mounted on the bar surface. And also we also make comparison between the measured strain and the applied load. So this can be used to calculate the axial force of the GFRP bar saw nails in field. And in field, we have installed two series of sensors on two different cell bars in field, and the total length is 32 meters. So after these very long bars were installed in these slopes, and we have to grout the borehole using cement grout, and finally we obtained the distributed strength of the two cell nails for 5 weeks. And we found that the cell nail were under continuous but limited elongation. And we also make comparison between the measured strain of fiber optic sensors and also and the conventional sensor, that is the strain gauge. And most of the data agree fairly well between the two types of sensors. And the last one is the measurement, the monitoring the strain change of anchorage cables in field. So very long, flexible anchorage cables were normally used to reinforce the foundation plates or slopes. And normally we had to conduct the pull-out tests to examine the pull-out resistance of this kind of anchorage cables. So in here, we also use the distributed fiber optic sensor, that is the BOTDA technique, to monitor the pull-out behavior of these kind of anchorage cables. And we have successfully obtained the strain distribution along the whole anchorage cables. Well, the other application is the gel grade monitoring. So this kind of typical structure was also used for the reinforcement of slopes or embankment. So in this study, it's a typical laboratory study. We just simply use IPG sensors to placed on these on the middle position of this gel grade to measure the strain change, and we carry out a typical slope loading test to obtain the strain change of this kind of gel grade. Well, the deformation of this kind of gel grade is very large. Normally can approach up to maybe 1% to 2% deformation. So in using IPG sensors, we can successfully obtain the very large strain change, but the conventional sensors cannot be used to measure the deformation of this kind of gel grade because the surface of this kind of material is very rough. The last one is the tunnel monitoring. So we have carried out a monitoring study of a tunnel in tunnel monitoring using fiber optic sensors in Dongguan in Guangdong province. So we just simply mount the fiber optic sensors on the steel cage of this tunnel segment. And in this study, we monitor a total of five tunnel segment ring underground. And the basic technology used in this study is the OFDR technique. And in this study, we successfully obtained the distributed strain change of this tunnel segment, especially after installation. The deformation of these tunnel segments may not be stable, and the very large strain change of this tunnel segment may indicate that the installed tunnel segment may not be safe. So the minimum spatial resolution in this study for strain measurement was 1.8 millimeters. So finally, we have obtained the strain variation change of the tunnel segments after installation in field, and we found that all these tunnel segments were under compression. But within around 2 months monitoring studies, we found that the maximum obtained strain change is less than 300 microstrain. And in comparison with the limited compressive deformation of this tunnel segment, so it's quite limited. So indicating that these tunnel segments were safe after installation underground. And we also calculate the average microstrain change in terms of the fiber optic sensors on these tunnel segments, we found that all these the initial deformation of the tunnel segments were decrease gradually against time, but all these data becomes relatively stable at around 40 days after installation work. So all these data curves were consistent in all these different tunnel segments. So next, I will make a brief summary and conclusions. And while we have used different types of sensors for field monitoring, including the BG, BOTD, and the BOFDR technique, well, in my opinion, that the measurement study of different structures and ground is difficult because the requirement for data collection of fiber optic sensors in field is very high. That is, for the geotechnical field is very dirty, and the monitoring environment is very tough. So this is the first point I want to highlight. The other is that the interaction mechanism between fiber optic sensors and different structures is complicated. So sometimes we have to mount the fiber optic sensors on steel bars, and sometimes we embedding fiber optic sensors in concrete. So the structure stream and the fiber optic sensor, there are a number of layers between the fiber sensors and also the external structures, like the protection layers and other layers. So the interaction mechanism need to be carefully investigated, especially in field for geotechnical monitoring. And so I'm from the University, so also from the underground policy of academic. UPA in University was founded by Professor Chen Jiangsheng, and also our aim is to protect and build a better ecological environment by utilizing urban underground space and the land resources effectively. So these are a total of 4 members of our research group, and thank you very much.
So thank you very much, Professor Hong, for a fascinating talk. The talk is open for a few minutes to any questions that anyone has. So if you have any questions, please just ask them, and that will be fine.
I have a question, Professor Ken.
Yes.
I hope you can hear me, Professor Hong.
Yes.
Can you hear me?
Yes, very clear.
Yeah, your talk is very interesting. I was just wondering whether we can have your slide. Would that be possible? That's my first question, whether we can have your slide. Would that be okay with you?
Yes, okay. I will send you maybe using email.
If I could ask for the same thing, that would be extremely useful. I'd be very keen to share them with some of my civil engineering colleagues at the university. So I think we both agree this is really fascinating work.
My next question, Professor Hong, we were doing some slope monitoring. We get some funding from Newton Fund from the UK, but at a very preliminary stage. What you have done is very advanced. Maybe we might need to have some advice or collaboration with you. Would that be possible?
Yes, I will be very happy if you can give us a chance to carry out some collaborative study. It's really very interesting for me. Thank you.
And my next question, I have this local company come to see us. We have a lot of these cable bridges, bridges being held by cables.
Mm-hmm.
All right, those steel cable hold the bridges. they want to measure the stress on the cable, but they give me a sample of the cable. All the cables are very tight. They are very tight. And how do you put your fiber inside those, cable, Professor Hom? Because they want to monitor those cable bridge for maintenance, because it's very costly. Whether it's the right time to replace this cable? Can you help us on that?
You mean these cables?
Those, you have seen. I think China will have these cable, bridges where it's being held by, cable. Right? Maybe there are about 100 of those smaller wire, but they are being held very tightly. How do you put your fiber optics over the cable, or you insert inside the cable?
For the cable you have mentioned, I'm still not very clear, but for the cables we have measured in field, it's just anchorage cable. We just simply use some clamps to fix these sensors on this cable surface. And we don't worry about the slide between the cable and the fiber optic sensors, because we have to ground these cables inside borehole using cement grout. So finally, all these fiber optic cables were, tightly fixed in a layer between the cement grout and steel. It's very tight. So we have carried out some, calibration tests. That is, we use the string sensors and also the fiber optic sensor to make comparison between the two measured string data, and we found that these two types of data curves were agree fairly well. So if you want to measure the string change of just a simple a steel cable, so you have to be careful, because there is a limited string of the fiber optic sensor that normally maybe 1 to 2%. That is the maximum string that fiber optic sensor can measure. So while the elongation may be very large for the cable you have mentioned, so I think this may be a problem for you.
Because the one that we have many cable bridges in this country, many.
Yeah.
So we have many, river, and those cable are pre-installed. It's pre-installed.
Yeah.
But they come and see us. Maybe Professor Ken would like to look into this, because there are many bridges in this country that require maintenance on the cable, but they are pre-installed, because they give me the sample in my lab. Maybe we can share with you one meeting, maybe next few days, or online we give you a picture of how the cable. How to insert? We have been trying to find a way to insert the fiber optics in the cable. The steel cable is a steel cable.
Yeah. Pardon?
It's a steel cable.
Yes.
Maybe we will share the photograph maybe at some other time, because now it's short of time, and then maybe you can see the cable, and maybe we can work together with Professor Ken, because they are very much in need in this country to monitor the bridges, because they have to maintain regularly.
Yes.
To change the cable. They don't want the bridge to collapse. They need to maintain and the cable constantly to monitor. Changing the cable can be very expensive. So they want to know exactly when is the right time to change.
Yes.
I think this is very important, because we have seen in the UK again bridges that are 50 or 60 years old, which have cables which are decaying, and so the bridges have been the total loading has been reduced, and indeed they have had to be replaced. So it's a major problem. But could I ask one final question, perhaps, before we move on? And that is, Professor Harith and myself are both essentially optical physicists and engineers. You are a civil engineer, and one of the challenges we have found is in getting our civil engineering colleagues to really really engage strongly. Clearly, in your university and in your consultancy work, you're really managing to bridge that gap between the optical physics and engineering and the civil engineering. So how do you persuade your civil engineering colleagues who are perhaps unaware of the benefits of optics that this is a really good technology?
Yeah.
What way do you do that?
Yes, thank you, Professor. It's a very good question. It's first, it's very difficult because the instrument and also the sensors are both very expensive. Well, I think in mainland China, one big advantage is that the consultancy companies require the application of new technology in field, and we have some fund to support this kind of study. This I think this is very good advantage for me, especially in Shenzhen.
Shenzhen is where innovation really happens in China. It's
thank you.
I think perhaps you have clearly managed to I suppose get that sense of new technology being a real advantage and overcome some of the conservatism in the industry. So thank you for that. So we've really run out of time, but we will be in touch with you. And
thank you.
It's been absolutely fascinating to hear some of the work that you've done. So thank you very much.
Thank you very much. Thank you.
So let's pass on to the next paper and the last paper of this session, and it continues the theme of fiber optic sensors and monitoring, particularly in the environment of civil engineering. So I'd like to call upon our next speaker, and our next speaker is known to everyone. It's distinguished Professor Datuk Dr. Harith Ahmed. Harith is a longtime collaborator of ours. He received his bachelor's degree in physics from the University of Malaya and his PhD in laser technologies from the University of Wales in the United Kingdom. So he began his academic career as a lecturer in the University of Malaya. He's director of the Photonics Research Centre, and as we know, he's been recognized both nationally and internationally in a wide variety of awards that he's received, including fellowship of the Academy of Sciences in Malaysia and the Distinguished Professor Award from the Ministry of Higher Education. All of those reflecting his distinction and the breadth of work that he's done. He's published extensively in fiber optics, in optoelectronics, amplifiers, lasers, and so on, and has over 500 articles in the major international journals. I think it's particularly important to note just how many MSc and PhD students have been supervised and gone on to extensive careers in the field across the world from Professor Harith's support, taking their PhDs. So we look forward very much to hearing about current progress on the project that he's involved with on landslide monitoring. I think, again, another great example of the use of optical fiber sensors in innovation in monitoring in the civil structural area. So over to you, Harith, to give your presentation. We look forward to hearing from you.
Thank you so much for the kind word, Professor Ken. And I just want to share with the audience, this project was being initiated actually by Professor Azizur Rahman and Professor Ken Grattan, and also Professor Gibato. All right. So this is a joint initiative. In fact, this is our second project. We have an earlier funding from Newton Fund on a similar topic, and this is the second, an extension of the project we have done earlier together with City University and Southampton University. What I'm going to do this morning, I think from this morning talk, Professor Hong have done so much work in this area, and I think we are just starting this particular area in this research center. We just want to update on the current progress in Newton-Ungku Omar Fund landslide monitoring project. Can we go to the next slide, Shamin? And my team members of this project is Dr. Muhammad Faizal Ismail, and our student, a PhD student, Muhammad Ashraf Alias, and Muhammad Shamir Muhammad Sa'ad, our PhD student. The outlines of my talk will be landslides that have occurred over the past 2 years. We have so many landslides in this country, and it's raining now. I think there will definitely be landslide taking place. And there are limitations on the conventional method that are used to monitor the landslide. And the fiber, our interest is to use fiber break grating technology for landslide monitoring. And then I will discuss the objective and the current progress and published work in this project so far. Next slide. Now, if you look at landslide, I think we have so many hills in this country, so many hills. And our hills are not like Hong Kong, where they are like Japan, they are rock-based. Ours are very soft soil. They are basically very soft soil hill. And when you have heavy downpour, the soil starts to move, and eventually it causes landslide that has claimed many lives. If you look at landslide that throughout the world, landslide has taken many lives, like landslide at Mumbai, India, July 2021. At least 30 people died. And landslide at our country, Fraser Hill, last year, there are 13 vehicles trapped, and there are few lives is lost. And then we have also at our eastern part of our country, Sabah and Sarawak, you have landslide at the Kinabalu National Park. You have 791 people from 217 villages who were displaced. So this costs life and costs money, asset to the country. So landslide is a very important event in this country. I think last couple of months we have many landslides, even in Selangor. As you understand, Universiti Malaya is in Kuala Lumpur, and in Kuala Lumpur and Selangor we have many hill slopes that around this part of the campus. In fact, in our campus, last couple of months, Professor Ken and also the audience, I will bring you around later to see so many landslides occurring in our campus the last couple of months. You can see all the landslides. So we are being exposed to many landslides. So there must be a step taken how to monitor to have an early warning system such that action can be taken. So these are the photograph. It shows you the landslide at Ampang. That is March 2022. At least 4 dead. Next slide. And then we the current limitation of conventional method, which can be based on electrical method, is it has a low stability and durability. Is prone to lightning strike, and it can be short circuit because they are electrical system. They will also encounter electromagnetic interference, and then large scale slope monitoring cannot be achieved because as been mentioned this morning by Professor Hong, fiber optics can be done on the large scale. You can place fiber optic on the whole slope of the hill. And the electrical approach can be expensive. I got some quotation for the conventional method. They are very expensive compared to the optical methods. So optical method is the way to go. It's a way to go in the future to have a very smart system such that the landslide of the hill can be monitored in situ and provide an early warning system. And the problem with the other limitation of the electrical method, it cannot be transmitted over long distance as compared to optical fiber. Because optical fiber are very well placed. We have optical fiber in this country for our internet services. You can write on them that can provide a long distance monitoring. Next slide, please. How do we solve this issue? All right, I think we are working hand in hand with Professor Ken, Professor Azizur Rahman, and Professor Jibato. They are very important member of the team, and also our student, Dr. Faisal, and also Shamil and Ashraf. It's quite a small team. I think we are trying to start this project. There's another university, Petronas are doing quite similar thing, and there are university technology. I think not that many people are working on landslide. So I think there are quite a small number here, but I think we know the importance of landslide and how to monitor landslide effectively. Now, how we want to proceed now. We can monitor the ground movement to form an early warning system, which we want to establish using Arduino, and then you use Wi-Fi that can provide the Wi-Fi signal that you can monitor on the heat slope if there is any movement using optical-based devices. We have found a slope. If you see this slope, it's next to physics building, Professor Ken. I will show you later. While you're having tea, this slope is next to physics building. You can see a big part of the hill is being carved, and you can put the sensor around the top of the slope to give you an early warning system. Now we have a lot of site in the campus to install our sensor, and the approach that we're going to do, like for instance, we have developed a extensometer, inclinometer, and also vibration sensor, for example. Next. Optical-based devices have some key advantage, okay? It's low cost because fibers are very cheap. And then we have our own facilities to fabricate fiber bracketting. We have excimer laser, about 2 excimer laser and other type of laser. And we just purchased a femtosecond laser writing system to write on fibers, because we find using excimer can be quite expensive because we have to replace gases. And then with this current conflict, we have conflict between Russia and Ukraine, because all the gases come, a lot of these gases come from Russia, and that can be quite difficult for us to obtain because of the sanctions. So femtosecond laser writing would be the way forward to write FBG. We have in our lab, I will show to Professor Ken, Gilberto, and so on. You can visit the lab where we have the laser. The other advantage, it has a high-speed response, immune towards electromagnetic interference, and ease of installation. I'm making the very gross assumption. We have not really put on the slope fully yet. Can perform remote long-distance monitoring, which is true, and can perform large-scale slope monitoring, as being presented by Professor Hong this morning. It is a very interesting presentation that we find that Professor Hong has done very extensively. Next slide. Now, I just go through quickly on the basic principle of FBG. Over the variety of optical sensor available, we have choose fiber bright rating as the sensing element of our device. These are excimer based. We use an excimer at a UV wavelength and using a face mask approach. And what we do, we shine the UV light and to cause 2 photon absorption. To create 2 photon absorption, we have a change of refractive index at the different part of the core. The pattern on the core is formed by the pattern on the face mask. All right, so different face masks will have different spacing. will give you a different wavelength reflection. So basically, if you have a broad light as given on this, if you look at my pointer, you can see my pointer, a very broad light here. And then as it goes into the FBG, a particular wavelength will be reflected. A particular wavelength will be reflected, and then the rest will pass through. By knowing this wavelength, if I stretch the fiber, I will shift the wavelength to another value. Then the shifting of this wavelength will give me the information on the stress or the strain occurring on the fiber. And these are example. If you look on the right hand side, is the unstrained FBG will give you a wavelength at certain value given by 2n over lambda. And if the fiber is being put under stress, strain FBG, the bottom figure, you find that the wavelength will be shifted slightly. This information of shifting of wavelength will give you a very important link to the stress or the strain occurring on the FBG. So the advantage of using FBG is not influenced by electromagnetic interference, free from electrical power caused by the insulation. It act as an accurate point sensor. 2 or more sensors can be connected in series. I have the opportunity to do multiplexing, and it's cost effective. Next. Now, the project is the project of the Newton Fund that we get, I think, last year, I think end of 2020. We are supposed to meet up with Professor Ken, Professor Azizo, Professor Dojibato, but because of COVID-19, we cannot travel, and we are so grateful with the present. They are actually Professor Ken, Professor Azizo, and Professor Dojibato are physically present at our campus. If we have a lot of students in this audience, if you want to take the opportunity, you can talk to them and exchange ideas. So the objective is to develop an optical-based sensor for slope and ground movement monitoring, to package this sensor ruggedly for the use in harsh environment and deploy for real field testing, to develop an early prediction remote monitoring landslide warning system. Next slide, please. So the current progress, we have published a lot of this work in IEEE sensor and other journal. The list of journal that we have published is in the last slide for students if they are interested to read a bit more. This was just a snapshot what we have done. So basically, if you look at this thing, we use a plastic pipe, and then you have FBG being placed on top of the plastic pipe. And then if you have a ground movement and you see in the red, if you have a pressure hitting onto the pipe, that will cause the FBG to be extended. This extension of the FBG will give you a shift of wavelength at different point of the pipe, and therefore that shifting of wavelength, we will know precisely where the pressure is being applied. Is it being applied at the topmost pipe, or is it at the middle point, or is it at the end point? So we will know precisely. And most of our sensor come with FBG being calibrated for sensing the temperature, because when you put in the outside and you put in the field, this FBG is very responsive to strain or stress, and also to temperature. So you have to calibrate. You have to have another FBG without exposing to the stress to provide you a shift in the wavelength due to temperature. So by having that FBG-T, we can offset that shift due to the temperature, and the shift due to stress can be obtained. So in this slide, a high precision extensometer system for ground displacement measurement using FBG. Prior to any landslide, the soil structure will change as it loses its cohesion, causing ground movement to occur. is highly important to monitor such event in order to develop an early warning system for landslide monitoring. An optical-based extensometer system was developed based on FBGs. Next, please. And this extensometer, if you look in this slide, we share to the audience how it's being done. This extensometer design comprises of few FBG-based strain sensor. This is a sensing element, as you see from this. Shami, we can bring the pointer to the FBG grating. You look, these are the FBG grating, and then they are being placed on the fiber are being placed wrap around a thermoplastic polyurethane. And then these are, if you look at this picture at the bottom left-hand side, you see how it's been placed on top of the pipe. So we have, in this project, we also have two 3D printer to make all these devices. You can see them in the lab. We are open to any student who want to use our 3D printer to do their research work. We are very open. We want to share whatever that we have. So if you look, we have a 3D printer. So we make all the device from A to Z in the laboratory. Now, material used in the material used are thermoplastic polyurethane, TPU. We have studied various types of polymer. We find thermoplastic polyurethane is the best material. It gives you enhanced sensitivity. Melt processable thermoplastic elastomer with high durability and flexibility. And the niche market are mostly, if you look at the 3D printer, they are in automotive industry, sport and leisure, tube and hoses, key behavior, excellent tensile strength, robust, weather and UV resistant, good flexibility over a wide temperature range. Next slide. Now, this is the extension of the earlier slide, just to give you a slightly more detail. It's very important for the sensor to have temperature compensation. So if you look at this slide, you see, if Shami can bring the pointer to the center figure. If you look at the center figure, you see the FBG for temperature compensation is being placed in the end of the tube in the cap, in the form of a cap. So FBG labels FBGT acts as a temperature sensor to correct any temperature effect that are present in the system. Its joint and joint cap are used to protect and fix FBGT inside the pipe. Next. So next is the extensometer design. If you look in this slide, we have the extensometer. It's a straight pipe, straight plastic pipe you can get from any hardware shop. And before ground movement, the pipe are straight. After exposing to landslide or any pressure from the ground, you'll find that it will cause some distortion to the pipe as given into the right hand in the figure. Those soil movement will cause a distortion in the pipe because they are plastic pipe, they are quite flexible, and then they will give you the distortion, and that distortion will cause an extension of the FBG that is being placed on the side of the pipe as being explained in the early slide. So this is how it works. It's quite straightforward for student project. If the student interested to venture into slope monitoring, is very interesting. It has in fact slope sensor are a very big impact to the country. Research is useful if you have great impact to the country. Is always useful. It helps to elevate the country problem. So FBG1 to FBG5 are placed on the PVC pipe towards the ground movement direction. FBGT are fixed inside the PVC pipe loosely, not to encounter any stress or strain, to prohibit it from detecting strain variation. The wavelength shift of the strain-sensitive FBG can be converted into displacement. Hence, we can monitor how much the ground moves. So this can give you a very important information before the occurrence of the landslide. So the experimental setup, lab and small scale field testing, laboratory testing. If you look, we have this pipe before putting into the field. We have the pipe in the lab and we put a pressure to bend the pipe. Means that we want to understand further how the stress on the pipe will give the shifting of the wavelength in the various FBG. We have about 5 FBG here, FBG 1, 2, 3, 4, and 5. So then on this bottom part, we have a force that create the pressure to simulate a landslide, and that will cause the pipe to bend slightly. I will use the word to bend slightly. It's not a major bend, and that will stretch the fiber with the FBG. That will provide us information on the force being applied to the pipe. Next, please. In small scale field testing, before we put into the slope, we're in the process of putting onto the slope because we need to have the permission from the estate office because the slope is under the purview of the estate office. They will not allow us to simply move to the slope because of safety, because of there could be more landslide taking place. So we have wrote they have no objection for us to put our sensor onto the slope. So in the next trip of Professor Ken, Professor Azizo, Professor Rahman, you can see this sensor on the slope next to our physics in the building. You'll see that. So small scale field testing, we also simulate. We have a box of. There's a box on the bottommost on your left hand side. There's a box frame. We build up the box, a wood box, and then we fill with soil. We fill with soil, a similar soil as what we have in the hill, a similar soil. And then we buried the pipe inside the soil. If you look at this, the left-hand side, the upper figure will give you the pipe is being placed in between the soil. And then we put different mesh at different point of the pipe. And then from there, we measure the stress occurring on the FBG, and that will give us a very important calibration. Calibration of your sensor is extremely important. We don't want to, at the end of the day, when we put into the slope, then you have a wavelength shift. You cannot even know exactly what are the force exerted at your sensor. So you have to constantly calibrate. So these are being done in great detail. If you look on your right hand side, this is how we have this temperature sensor, and then we have the fiber optics connector. They are being tested in both dry and wet soil. Okay, we have one time we have dry soil, we test that, and then we pour water of the right volume and right density to cause the soil to be wet, and then we repeat the measurement again to see the effect of the weight onto the sensor that's been buried in the wet soil. Next slide, please. Okay, these are real pictures of the setup. If you look carefully on your left-hand side, these are the pipe, the PVC pipe, and the yellow tape are those FBG sensors being placed on one side of the pipe. And then if you look at the insert, in the insert, you see how we place the sensor around the tape. And then these are being, after we have done the lab calibration, then we do again for field testing to the actual soil. These are the soil that you will see in our slope. They are normally red color in soil. They are soft soil, actually. They're basically soft soil. And then if you look here, there's a weight that we put. And then if you look at the arrow, this gives you the position, different position of the FBG at one end of the pipe, FBG 2, 3, 4, and 5. And the weight is being placed at the center. And then we'll see the movement of the wavelength of FBG 1, 2, and 3, and 4, and 5. You'll find that the FBG 3, because the weight is on top of it, you'll find more displacement compared to the FBG that's far from the center. Now, by having this shift of wavelength, it's very interesting to know the force that being experienced by the fiber break, creating due to the weight onto the soil. Next slide, please. Now, these are measurements that I will not go into detail because they are also in our publication. So for those who are very interested, you can refer to our publication. We provide a very detailed paper on this approach. And if you look at the first graph, it's called the laboratory calibration, right? And then it can be seen that FBG gives the highest response of 0.036 nanometer per cm due to its ITS, its position exactly at the bending point. So you find that because the weight are being put at the force are being applied at the center, so the FBG3 will experience more displacement compared to the other FBG. And this is the temperature sensitivity, which has to be calibrated. They are very important. All right, next slide. So example of our extensometer response based on FBG3, we have done extensive measurement on dry soil. What will happen to the displacement? You find the FBG3 experience more displacement due to the strain that is on top of FBG3. And you find that FBG1 and 2 will have less displacement compared to FBG3. And the next graph on your right-hand side provide the extensometer length against wet soil. Your left hand is dry soil, is wet soil. And the bottom two graphs indicate the displacement. The two upper graphs give you information on the extensometer and the displacement against strain, and then this the bottom two graphs provide displacement as you have different point of your fiber bright creating. These are for dry soil, these are for the wet soil. Next slide. So the one important, as I want to stress, is temperature compensation is very important. So what you want to do is to have FBG that is temperature independent, right? The extensometer should be temperature independent. These are being offset by the temperature sensor. So temperature independent FBG based vibration sensor are very useful for to measure also soil movement. And this approach I want to share with the audience on the slide are Fabry-Perot interferometer approach. Prior to any landslide, the soil structure would change actually, and this will cause seismic vibration inside the soil. It's important to monitor this parameter in order to develop a landslide early warning system. So what the country need now, an early warning system actually. So you cannot prevent landslide from taking place. You cannot prevent. If the soil is soft due to rainfall, the soil do not bind or bond itself, together. It get loosened, and then the soil will start to move, and then it will cause a landslide. You cannot prevent actually, but you can create an early warning system, maybe a few hours before any serious landslide, to move people away from the slope. If you have the slope at the highway, you can prevent the car from approaching the road length that may cause landslide. We are currently developing a temperature independent vibration sensor based on FBG based Fabry-Perot interferometer. Next slide, please. And these are all the measurements that we have taken. You see the similar spectrum as in the early speaker, similar. And people like Shami will be able to explain so much well. And some of the example that we took from the paper here, landslide, seismic, magnitude, Earth, and also planetary science letter is appear in the journal Earth and Planetary Science letter. The data on your left hand side shows that landslide occur at low frequency region, high in magnitude. So normally landslide takes place at low frequency actually. So if you are able to detect the low frequency part, you can have an early warning system. So landslide takes place at low frequency but high in magnitude. Next slide, please. So these are the experimental setup. It's a very simple experiment that Sharmi has done and he has published the paper. It's just composed of ASE source, 980 nanometer laser diode through WDM and erbium doped fiber to provide a broadband source, amplified spontaneous emission. And then you have the FBG, and this is FBG Fabry-Perot interferometer, the one at the bottom part. And then we use 3-port circulators at the left and the right. And then we have a photo detector to an oscilloscope. And then we have a signal gen to generate or to create acoustic waves to simulate the seismic movement actually. Next. So these are what we get in the measurement. It appeared in our paper. I think for those who are interested can also refer to this. Due to short of time, I will speed up my talk. Can we go to next slide? No. Okay. This is how the FBG. Can you go before? Don't move too fast, Shami. Okay, next slide, please. Okay, this is how it looks like. We also developed FBG-based pressure sensor for soil monitoring application. It looks like this. These are being done by 3D printer. The FBG is being inserted into a hole from one end to the next end, and then they are being glued using aerolite to make sure there's no movement. So when you apply a force on the top, that will cause the circle to extend, and that will cause increase of length in the FBGP, and that will give you a shift of wavelength. And this is how it looks like on your right hand side. This is how you apply them. Okay, next slide. And we can make 2 by 2. If you look, Shami has done many of these in the sensor in a 2 by 2 is 2D matrix. So we have many sensors. So any force being applied at any point on this base will tell you precisely which of these sensor will experience the stress or the strain. Next. So the other one that we are doing is called a fiber breadth grating based inclinometer probe with enhanced sensitivity for higher slope, the profiling resolution. This is what we are doing now. If I'm not mistaken, it consists of 3 sensors within 70 centimeter in length, and these are in the lab. Those who are interested can all look at this in the lab and see how it's been placed. These are the new development that we are doing now. Next. So for this work, main sensing element is here. We have a detachable TPU-based middle shaft, and then you have the detachable socket, and the FBG are being placed glued onto the shaft. And these are the main sensing element that you see in the earlier slide. We use different material as the middle shaft, which is thermoplastic polyurethane. Increase in why we use TPU. You can use TPA, but it's a bit rigid. It's not so sensitive. So TPU is more sensitive. It provides increase in the sensitivity, increase in the resolution. That will detect precisely any pressure onto it. And we have done, I think, quite pretty well. These are the paper that we have published, but I think some of them are in IEEE sensor, and then sensor journal from MDPI, and there are, I think, about 4 papers under review now. So we hope by the end of this project, we have filed a patent. It's been filed already, and we hope at the end of this project we will have about 12 publications that will help in the student PhD thesis. Okay, the next slide. So thank you, Professor Ken. My sincere apology for extending the time. I am willing to take any question if there's any question.
Great, thank you very much for a fascinating presentation on the work that we have done and the really the very interesting applications that relate specifically to a problem here in Malaysia. So, as Haritha said, the paper is open for questions. Does anyone have any questions?
Students let them ask questions. There's the irony behind here.
I think the only question from me really is just what do you see as the next step in this work? What do you think are the next set of problems that we can tackle with this technology?
Because I did mention just now, there are a few company approaches us, Professor Ken. One is the cable bridge and then the tunnel. We have many of these overhead rapid transport system actually. So when they go through the tunnel, they like to measure the stress on the structure as being shown by Professor Hong just now. These are the requests being by the industry. If you are interested, we can look at the opportunity. I think there are a lot of future consultation work in this country, Professor Ken. But for our work, we have communicated with Selangor and the government. We wanted to put this sensor on the slope in Selangor.
Okay, thank you. Arif, I see you have a
Yes.
question, so please
Thank
follow.
you. Thank you. Thank you, Professor Harith. A very fascinating talk. One question is, when you detect the landslide and you place that tube of FBGs, at what depth do you place it? And do you place it horizontally or does it go down vertically?
It go down, vertically, Prof.
Okay. And typically, how deep do you take it?
It would depend on the hill. Some of our hill are not very high. We have the only strange thing, Professor Aru, we have a lot of hills somehow, but they're not very high. So you can put maybe midway, depending maybe about 5 meter down from the top or more, because the hill are not that high actually. So the other thing that we would like to do with Professor Ken is to put the mesh of this sensor onto a slope. That will tell you precisely every point, because they need to know which point really start the initial soil movement. You need to know the first point. Once that takes place, then landslide will just happen throughout.
And typically, does the sliding take place from the top surfaces or does it start at the deeper lying layers?
I think from what I see, I can bring you out to see the slope we have here next to us only. I think most likely is to start from the top. It start to when the rain fall. I would suspect there are more rain deposition on the top before it go down to the soil. So it start from there, and then the rainwater. If it, of course, here it rains very heavily, Professor Aru. I think this morning you can see the rainfall if you are in the campus. It's a very heavy rain. Sometimes it runs for 6 hours. Heavy rain. We don't have like in UK. UK you have rain, but they are very fine rain. But you do get wet. You do get wet, but it's not intense. In this country, the rain are very intense. So after 1 hour, 2 hours, you find the rain will start to penetrate down to the hill that will cause the soil movement. Because we are not rocky, we are mostly soft soil, Professor Aru.
Yes, I come from originally a soft soil region myself, so I can understand that. Yeah, thank you very much. Thank you, Professor Grattan.
You're most
Thank you.
welcome.
Thank you. I think we're probably really run out of time, and I know the session has overrun, but it has overrun for very good reasons because of some very interesting talks. So I'd like to close the session to thank Professor Harith and Professor Hong for the presentations they've given, and ask you to take a break and then join us again for the next session. So thank you very much for your attention.
Thank you, Prof. Grattan. So I think we will continue this session with a technical session. Okay, my name is Muhammad Faizal. I will be chairing the next 3 sessions before. So the first session will be before we have a break. So may I know whether Dr. Ahmad Shukri is with us today for the presentation? Dr. Ahmad Shukri, or maybe he's the representative for his group. There's none. We can I think we will continue our sessions after the break, and the session will start at 11:45. We just take a break now since that Dr. Muhammad Shukri and maybe his team is not with us today. Or maybe they face some difficulties or issues in terms of technical issues. So our session will continue at 11:45 with the presentation will be by Nadratul Huda Misral and Siti Aisha Hasbullah. So we will continue at 11:45 afterwards. Now I would like to invite, let's say you are in the Photonics Research Centre, we have some refreshment in the first floor of a physics lab, physics department. Okay, that's all. Thank you so much. See you at 11:45.
Dr. Huda, cuba share screen.
Okay.
Share. Okay, move second slide. Okay, introduction. Next, introduction. Okay, bernampak. Good. Guna laser pointer.
Okay, clear?
Clear. Laser pointer pun okay. Okay, bernampak.
Thank you.
Okay, good morning, everybody. Welcome to the technical sessions for this morning. For the first presentation after this break, I would like to introduce you Dr. Nadratul Huda binti Misra. I think she is from Tahmidi Centre, Universiti Sains Islam Malaysia, USIM, which is, if I'm not mistaken, in Malaya, Universiti Malaya. And for this paper, or for this presentation, her partner will be Associate Professor Dr. Siti Aisyah binti Hasbullah, who is from Department of Chemistry, Faculty of Science and Technology, Universiti Kebangsaan Malaysia. So the title of her presentation is Reflectance Chemosensor for plumber, we have mistaken, ion based on bis-indole methane derivative. So I would like to pass over the session to Dr. Nadratul for the presentation. Okay, Doctor, please welcome.
All right, thank you, Mr. Faisal. Bismillahirrahmanirrahim. Can you hear my voice?
Yes.
All right. Okay. Assalamualaikum and a very good morning to everyone. So my name is Dr. Nadratul Huda binti Misral. And today I'd like to present my current research project entitled Reflectance Chemosensor for lead ion based on bis-indole methane derivative. So I'm from Universiti Sains Islam Malaysia. Okay, so as we know, this sensor is based on bis-indole methane. So indoles are natural organic compounds which have a bicyclic structure, and due to the presence of an electron-rich chiral moiety, it's normally used for the development of new biological active derivatives. Besides, it also has gained researchers' attention in its capability to act as the ionophore in heavy metal sensor. And for the problem statement, accumulation of heavy metals in agriculture soils through wastewater irrigation is very dangerous, as it could be a major environmental health problem, as it induces neurotoxic effect. Plus, many conventional methods used for heavy metal detection are having several drawbacks, and therefore there is a need in developing a simple-to-use device to overcome the highlighted issues. Therefore, in this study, we focus on using indole molecule for the development of optical lead ion sensor using poly and butyl acrylate as the matrix. The hydrophobic poly NBA acrylate, or we call it as poly NBA, is a non-plasticizer polymer with low glass transition temperature and exhibits a strong addition to the substrate surface, which could substantially improve the analytical sensing performance. Hence, with the use of poly-NBA as the matrix, it is expected to help the whole sensor system in quantifying lead ion. Okay, so these are the process involved in developing the heavy metal ion optical sensor. Begin with synthesis of this indole methane and also the characterization of the compound. And then we conduct computational study, which involves HOMO-LUMO analysis and also MEP generation. And after that, we conduct binding study using UV titration. It focuses on study the interaction developed between the metal ion and also the ionophore. And after we confirmed the interaction between the ionophore and also the metal ion, we will proceed to the development of the full sensor system, which involve fabrication of optical lead ion sensor, optimization and performance study, and also the real sample analysis. So today I would like to present the first part of the study, as the second part of the study is still in progress. Okay, in this study, we implemented a facile one-pot condensation reaction between substituted indole and benzaldehyde in order to yield derivative of these indole methanes. So this synthesis method was previously reported by Imran and his group of research to produce this indole methane, which has a good biological activity as carbonic anhydrase 2 inhibitor. However, we don't want to synthesize indole which act as the carbon anhydrase inhibitor. We want to use indole as the ionophores. Therefore, in order to employ the same objective of yielding this indolent methane using a feasible and simple pathway, so the same method was implemented upon minimal modification, which we're extending the reaction time to 18 hours to afford a higher percentage of yield. After we synthesize the indolent methane, we proceed to the characterization process. And as we confirm the structure of the compound that we want, we conduct the computational method, which involve two types of analysis. Okay, so the first one, using HOMO and LUMO energy value, a molecule that has a lower value of FMO's energy gap, which the difference between HOMO and LUMO energy value generally associated with a high chemical reactivity, high polarizability, low kinetic stability, and also termed as a soft molecule. And the value of HOMO orbital also provide a good information related to electron density possessed by a molecule, in which a high HOMO value demonstrate a high energy and reach of electrons that can interact with the metal ion. Therefore, this HOMO and LUMO energy value and also the FMO's energy gap is comparable with the previous literature, which shows a good value of HOMO and LUMO and also the FMO's energy gap. Besides, we also conduct the MEP analysis, which is molecular electrostatic potential. And here is the picture of electrostatic potential surface mapped on the ligand. Okay, we can see the ligand demonstrate a slightly electron-rich area, which is in red color, with the negative potential region is localized over the electronegative atom of oxygen, which is this is hydroxy group, and the aromatic ring. So this negative electrostatic potential site is more favorable for the attraction of electrophilic species, which predictably to make interaction with the metal ions. So basically, the computational analysis is to confirm or to expect which area that the interaction might occur. Okay, the interaction between the ionophore, which is this indolent methane, with the metal ion. Therefore, based on the computational evaluations, this ligand was then proceeded to the colorimetric sensing analysis. Okay, colorimetric sensitivity of ligand bis indolent methane was monitored basically using human naked eye towards various heavy metal ions as shown in the picture. So we can see there are 7 types of metal ion. And from here we can see the most intense color change can be observed after the addition of colorless lead ion into the ligand solution, which is in yellow color, and it converts to orange color. So the distinct color change recorded indicated the ionochromic behavior possessed by the ligand towards the lead ion. To support the interaction between the metal and ligand, further analysis with regard to its binding affinity towards the selected lead ion was examined via UV titration. So from the UV spectrum of the free ligand without the metal ion, an important characteristic can be observed as there is an appearance of a small broad absorption band, okay, which indicates the existence of an intramolecular charge transfer, ICT, okay, associating with the nitrogen atom, and in this study is referred to the pyrrole moiety particularly. And we can see here, okay, throughout the titration, the absorbance intensity of the band involving ICT showed a hypochromic effect in which it decreased gradually after it indicate a spectacular depletion when we add the first drop of the metal ion and followed by another drop by drop, okay, and it shifted to a longer wavelength as a new band, okay. So this effect, we call it as a hyperchromic effect, okay. We can see hyperchromic effect in the new band, which can be classified as DD band, that demonstrated the coordination between the ligand and lead ion. So as we did the titration, the ICT band become smaller and it shifted to a longer wavelength as a new DD peak, which indicates the interaction between the ligand and also the lead ion. The value of association constant, Ka, was calculated from the Bennessy-Hilbrand equation, which shows one-to-one complex formation. And we also did the FT, which is computational calculation, to confirm and to understand the binding mode between ionophore, the ionophore, which is bis-indole methane, and the lead ion. So in the figure, we can see it is clear that lead ion occupied one of the pyrrole moieties of ligand BIM, which is bis-indole methane, through its carbon atom. The developed interaction hence allowed the ligand to hold the metal in just the correct orientation. So these studies have given a significant insight in supporting ligand bis-indole methane to be utilized in the development of metal ion sensor with respect to its potent binding behavior and interaction towards the lead ion. In conclusion, bis-indole methane acts as a good ionophore towards lead ion based on the binding study via UV titration and also the computational studies. And the use of NB as the metric is expected to substantially improve analytical sensing performance. And the depth of this optical sensor based on bis-indole methane, BIM, is expected to have a good limit of detection. All right, so thank you to Universiti Kebangsaan Malaysia for the main research, Universiti Teknologi Malaysia for the DFT analysis collaboration, and also University Science Islam Malaysia and KPM for the for sponsoring the whole study. Okay, with that, thank you.
Okay, thank you, Dr. Nadratul Huda, for the very insightful presentations. Therefore, I would like to open the session to Q&A. If let's say if there is any questions for Dr. Nadratul, if there is any from the participants.
Hi, Dr. Huda. I'm Amir from Department of Chemistry, Universiti Malaya. Yeah. Can you go back to the slide number 8?
Slide number 8.
Yes. Yeah, the binding itself, the lead ion is purposely attached to the carbon, right?
Yes.
Is it possible to attach to other lone pair nitrogen base there?
Yes, actually, at first we expect it to bind through the lone pair. Through the nitrogen atom, because that's why we use the pyrrole moiety or indole moiety itself. But then when we conduct the DFT, it proposed. So DFT proposing that lead ion will be attached to the carbon atom in the pyrrole moiety. So it's still in the pyrrole ring. I mean the lone pair from the nitrogen is still circulating the ring. So it is possible that this is from the lone pair itself. I mean because the electron is circulating the circle, and then it's possible to make interaction there.
Okay. But that one is confirmed by the DFT, right? The computational study, right?
Yes.
Any experimental results?
Okay, for experimental results, we did the UV titration. So actually, this broad absorption band here, ICT, okay, so it's around 400 to 500, 488, I think, nm. So it's generally associated with nitrogen atom. I mean, this ICT, intramolecular charge transfer absorption band, is normally being related to nitrogen atom. Any molecule that contains a nitrogen atom, so it will be small broadband ICT. ICT band. And after we did the titration, it is proved that this ICT becomes, I mean, it's hyperchromic. Okay, it become lower, and then it shifted to another wavelength. Okay, so this is the DD band, and from here we conclude that so the molecule itself interact with the lead ion through the nitrogen atom, but it is not specifically with nitrogen atom. It is molecule that contain nitrogen atom because it will have IC band. So IC band is related to molecule that contain nitrogen atom. So that's why we support it with CFT study, and we conclude might not bond to the NH itself. So it bonded to the carbon, but still in the pyromoiety which contain nitrogen atom.
Okay, got it. Okay, thank you, Doctor, for the clarification.
Okay, very good question, Muhammad Amirul. Do you have any other questions? We have 5 minutes more for the participant to ask if there's any query for Dr. Nadratul. Anybody? So I have one question, Doctor, regarding your presentation just now. So I'm not a chemist, but I try to understand what have been presented just now. I assume that one of the experiment conducted is, let's say, you drop or metal solution, right? Heavy metal solution on the ligand. So in terms of applications later on, do you need any substrates to host the ligand, or if there is anything in terms of developing the probe of the sensors?
Okay, so in developing the real sensor system, of course we need, if in this case we call it as matrix, so we need matrix to hold the compound to detect the metal ion. So in this project, I plan to use a polymer, non-plasticizer polymer, which is called as poly-NBA. So this poly-NBA will act as the matrix to physically hold my compound, my synthesized compound, and then it will detect the metal ion. So that's the idea.
Okay. Okay, if there is any question, thank you so much, Dr. Nadatul, a very good presentation just now.
Thank you.
Okay, and if let's say if you have any question besides this session, maybe you can contact Dr. Nadratul. I think we have her email over there and also her phone number, which is shown in the screen currently. Okay, thank you so much. Thank you so much. Okay, for our next presentation, I think we have a presentation by Okundalai Uluwasun Olumide. I hope that I pronounced your name correctly. Okundalai, if you are with me, if you are with us today.
Yes.
Okay. Okay, I think you are a PhD student in the University of Malaya, or you are a staff?
Actually, I just concluded my Viva, just received the Senate approval.
So congratulations to you.
Thank you very much. Thank you.
You are in the Institute of Mathematical Science, right? Faculty of Science of UM.
Yes.
And I assume that Professor Wan Ainun Mio Osman is your supervisor.
Yes.
Okay, the title of to be doctor, I can call you Dr. Pakundalai, is an efficient approximate solution of a nonlinear fractional order Schrodinger equation from optical sensors. Okay, I would like to give the sessions to you. You may present your slides now.
All right, thank you for having me. Slaman Tenga Ara Semua. Good afternoon. Actually, it's 5 a.m. in Nigeria. I'm in Nigeria now. Please, can you hear me very well?
Oh, yeah,
can I continue?
Nigeria. Okay, we can hear you clearly.
Yes. Thank you for giving me this opportunity. I also have to thank the chairman of this organizing committee, and then my fellow researcher. I need to thank them. My name is Oluwaseun Olumide Okundalaye. The title of my presentation is an efficient approximate solution of a nonlinear fractional order Schrödinger equation from optical sensors. And then these are the outline of my presentation. And then from the introduction, that is fractional calculus is a generalization of an ordinary differential and integration to an arbitrary non-integer order. That is, the integer order has been widely exploited. That is, integers start from when n equals to 1, 2, 3, 4, and like that. And then the non-integer is the values in between two integers, like 0.5, like 1.5. Begin to see that this study is highly limited. But this study started in 16th century by L. Opiter, asking a question from a colleague, friends in research, that what if the order will be n equals to 1 over 2? 1 over 2 is a non-integer. And then Lesbins replied, L. Opiter said, it will lead to a paradox from which one day useful consequence will be drawn. And then since 16th century to 19th century, a lot of researchers talking about Gottfried Leibniz, Isaac Newton, Joseph Fourier, and Niels Abel. A lot of researchers has already done an exploit. Currently now we have up to 40 fractional operator in existence that is using in mathematics, which is helping this area to gain a lot of attention from researchers. And then these are the areas of application. That is, we have it in tissue alteration in pathological state. That is the optical. That is the optical sense. And then we also have it in dynamic system. We have it in signal processing. We have it in genetics. All these areas are the application of a fractional calculus. Quickly, I would like to talk about the latest update on fractional calculus. It has rendered a new dimension and gave information in between two different integers. That is, what happened between integer 1 and integer 2. Is there any other, that is, what happened when the integer is 1.1, 1.2, or what happened when it's 0.9, 0.8, and then what are these information that really the behaviors, the performance. It also provides an accurate solution that better describes a non-linear reward. And then the third thing, which is very, very important, is as a non-linear operator, in sense, it considers the fact that the future state not only depend upon the present state, but upon all the history of the previous state. And then the latest update on non-linear Schrödinger equation. That is, a non-linear Schrödinger equation can be used to describe various complex and non-linear phenomena that arise from different fields of science, such as optical fibers, hydrodynamics complex, acoustic, and then many. And then the theory of optical soliton is one of the interesting topics for the investigation of soliton and propagation of a non-linear optical fibers. And then the third thing that is very common now is the optical soliton restrain electromagnetic wave that stretch in a nonlinear dispersed media and allow the intensity to remain unchanged due to the balance between dispersion and the nonlinearity effect. And then these are the literature review, the recent literature review on this area. That is the recent study from 2018, and then homotopy analysis was used. And then this one is a Liouville Caputo sense, is a fractional operator. And then in 2019, MITAG, that is they use a MITAG lefter to study this model using a modified expansion method. And then in 2020, we also have Caputo, we have Antagana, Belau, which all these ones are all approximate analytic solution. But this area is still open, which is conformable derivative operator, using it with a multi-stage optimal homotopic asymptotic method, which is still open to study. And then from there, these are the literature review on the approximate analytical solution right from 1953 to 2020. And then the motivation of this study. That is, there has been an imbalances as to whether an approximate solution of a nonlinear Schrödinger mathematical model will converges. That is also another motivation is that there is a need to enhance the convergence series of the solution for accurate approximate analytical solution. An approximate analytical solution is used where there is not an exact solution. Where there is not an exact solution to a particular problem, an approximate analytical solution is very, very advisable. And then the third motivation is to explore conformable fractional derivative operator with the intending method, which we call Mohan method in fractional calculus. And then these are our research methodology. We start with a literature review on this model, and then we propose the method, and then the method is constructed with conformable mathematical model, and then we write the code in a Maple code, and then the Maple code will help us to analyze the behavior, the performance, and the mathematical representation, and then the proposed techniques will produce a good result. And then the general solution of this approximate method, that is giving a series solution, that is we have sk, t, cj, which is equal to sk of 0 of t plus summation of I to n sk of I t, cj. This cj is called the control convergence parameter. That is that we take this series solution to converge very, very fast. And then if rk of t, cj equals to 0, then this solution, this one is there, which our solution is the exact solution. But thus doesn't exist a non-linear problem. So what our proposed method contributed to the previous analytical method is that by using an optimization techniques that we call the Galerkin's, that is given to the HK, is being substituted under an integral sign with the series solution here, and then from there we're able to generate an optimal value that we take this series solution to convergence. And then the formation model, the model formation, that is the fractional Schrödinger-Erother equation with a truncated derivative is given in this form. As rightly said that this model is a nonlinear model. So the target here, before this area is only given by an integer. So we try to transform this integer to a non-integer. That is then this form, so it will be represented by a fractional part, where the psi is a complex value function of x and t, which is a nonlinear of a partial differential equation, and the coefficient lambda, psi, sigma, and a are the group of the velocity. That is, so this model will be solved with the intending model. Actually, we are still working on the result, but our expectation is that the method, the intended method on this will converge due to the inclusion of optimization techniques, which will take us to convergence point very fast. So the expected result in this study, the dark bright and mixed dark bright and the singular optical solution to the fractional Schrödinger-Erother equation with conformable will be efficient with multi-stage optimal method. Why? Because the previous methods couldn't establish a formula that will take the control convergence parameter to a convergence. So due to the inclusion of the optimal techniques for accuracy and convergence. And then the second expectation is that the definition of the new fractional derivative, which we are proposing, which is conformable derivative operator, will be smoothly used in transforming the Schrödinger to a non-linear ordinary differential equation that will be very easy for us to solve. And then the third thing, that is the modeling with fractional differential equation has more advantage than traditional order, because the traditional order, which is we call the integer, is always limited to integer 1, integer 2. And then so that we'll be to study the memory, what happened between integer 1 and integer 2, and then also between integer 0 from 0 to 1, which is between 0 and 1, 0.5, and then it will give us a broad knowledge, and then the behaviors, and then the performance. So in conclusion, in this study, the Mohan will be used to find the approximate analytical solution for the nonlinear fractional models. It is worth mentioning that the Mohan finds solution without any discretization. That is, all others, the previous others method, approximate measure, they use discretization. That is, they need to discretize. But this one, doesn't use discretization. It's a very efficient method, and then the expected result may be useful in explaining the physical meaning of the study of a non-linear model. Those linear model that can't. The physical meaning is yet to go. This method can be very, very applied. Thank you for listening.
Thank you, Dr. Oluwaseun. Okay, I open the sessions to the participant. If let's say you have any question for the presenter. If there is any question, because the work presented just now involved a lot of mathematical stuff, Dr. Oluwaseun, and most of us here are physics and engineering. With the physics and engineering background, of course, we use a lot of maths, but not that extensive. We just apply the simplest one for our application.
Thank you.
Are you in Nigeria now?
Yes, I'm in Nigeria now.
So you did your Viva while you were there, or you just came back to Nigeria recently?
Actually, I left last year. I did my Viva November. No, yes, I did my Viva December last year from Nigeria, and then I had my Senate approval February. So I'm waiting. Actually, the convocation is coming by October, so I'm still yes.
Yeah, okay. It's still a long way to go for the convocations. 3 months more.
Yes.
Let's say if there is no questions from the participants, I would like to adjourn this meeting for a short break. Not for a short break, actually, for a lunch break. We will continue with our session later in the afternoon at 2 p.m. Okay. So I will see you soon, everybody. So we will start our session at 2 p.m. this evening. Okay, thank you so much. Thank you.